presentation is installation guidelines, practices. We do a lot of designs, and we see a lot of guys calling us after the fact and saying, hey, this doesn't work, can you help us out? And we can, but we go through and confirm these things first, because if you didn't do some of these basic principles, installation guidelines and practices, that's probably why you're having some of these problems. So good information for designers to think about, but for installers, for sure, you need to really follow basic principles, not to cut corners. My boss always told me, don't cut corners on design, because they're going to cut corners in installation because they have to. Sometimes the physical building won't let you do exactly what we thought, but we're going to try to design it as best we can to make sure that everything goes in according to plan. So we're going to talk about wet systems, high mass systems. That was one of the first questions when I started working for Legend Valve. My new boss said, have you done any radiant? I said, oh yeah, sure. He goes, wet systems or dry systems? And I was like, I don't know, So wet systems, anything that's going to have cement poured over the top of it, that's a wet system. The very high mass, concrete slabs, overpours, things like that. And the dry systems are low mass. Above floor systems, staple up from below with the heat transfer plates, those are all dry systems. And we're also going to talk about pipe layout guidelines. That's probably the area where I think I see that most people just don't lay out pipe the way that I would. And sometimes you get them into trouble and sometimes nothing happens. But if you follow the best practices, you'll have better success. So one of the things we want to talk about is floor coverings. That's a big deal. A lot of times when we're in the design stage of a radiant project, we're just trying to get a budget quote out so you can have some number. And we're giving you basic numbers, something that's theoretical but probable. But that floor covering makes a big deal. Loop CAD, if you were there earlier this morning, we had a Loop CAD presentation on how to use that. We go with like a 0.5 R value of resistance through a typical floor covering is what it defaults to. So when we find out, we designed it, here's your flow, here's your water temperature, and then somebody puts down, shag carpet with padding on top of that, and the R value instead of being 0.5 is 5, we're going to have issues with it. But at the design stage, we might not know what that floor coverage is going to be. They might say they want this, and then the custom home gets to a certain point, and they're cutting the budget, and they switch it to this. And just know, one of the best practices is, hey, here's what we thought it was going to be. We're getting ready to do the finish. What are those floor coverings? Let us talk to the designer, because we can easily plug in a different floor covering when we do a design. If it's an R5 that's calculated, and it's an R.75, we can plug it into our Loop CAD system. It'll give us a new flow rate, a new water temperature. It may not make much of an effect, but it could. So knowing what that floor covering is a big deal. Tile and stone, it's not the same R value across the board for natural stone versus man-made tile versus ceramics versus all of the different types of floor coverings there are that are stone or tile. And the way that they install it, are they going to put it down with glue? Are they going to put it down with a mud bed? Are they going to put it down with any kind of a cement board over the top of that? All of that adds up to resistance values, and we should know that. Maybe not for the budget quote, because we don't know what it is. We're going to calculate an estimation there. But when you get to that final stage where you're getting ready to do some installs or you're getting ready to do some commissioning, find out if anything's changed from what we designed, making sure that we can accurately heat that the way we thought we were going to. Hardwoods are a big deal. Years ago, they would say don't ever put radiant underneath hardwood. Well, the radiant systems we're using nowadays have such low water temperatures. Using hardwood's not a big deal. But there are manufacturers' maximums for surface temperature. Anytime you're using a hardwood floor, you should consult that manufacturer and find out what their maximum surface temperature is. Some of them are 85, most of them are, but if you get a manufacturer that says the maximum water or surface temperature I want is 80, and we design it to 85, and something goes wrong with that floor, as an installer, you're going to be in trouble. The designer's probably going to be in trouble. The wholesaler's going to be in trouble. Your cousin Vinny that told you about the project, he's probably in trouble. So, hardwood floors, definitely you want to look at the manufacturer's recommendation for that. Tell your designer, we plug that information and we can tell the system don't go over 80 degrees surface temperature. And it will calculate it out. It will tell us if we got enough BTUs with that lower surface temperature, and if we can't, it'll tell us we need supplemental heat. And we can easily think about that ahead of time rather than after the floor is installed and we got issues with it. So hardwood's a big deal. Making sure you know the construction, especially if it's a retrofit. You know, this is a typical, maybe a 2x10 and a subfloor here. We did a project one time where they ended up putting sleepers in and putting another subfloor above that. Don't know why, but they did. And then they were putting hardwood on that, and we were going to try to heat with heat transfer plates from below. We didn't know this existed. Luckily, I think the contractor was doing something near the stairs, and he was like, whoa, what's that? And we started looking at it. You know, we know what the R value is of 3/4 inch plywood. There's a chart that tells us what that is. We know what the R value of hardwood is based on what it is. We can add those up and we can calculate a resistance. I have no idea what the R value is of that air gap with that in there. It's kind of an unknown. We can make a guess at it. But wouldn't you feel bad if you put in heat transfer plates, charge that customer all this money, you turn the system on, and you don't get the performance you want?
Maybe with 180 degree
Just
water, it'll make
keep raising the water temp up, keep raising the water temp up, and eventually it'll heat. And that's not our goal as designers. Is we should know what the construction is of that floor before we commit to putting radiant in there. Especially if it's new construction, I would hope that wouldn't happen, but you never know. So you should always confirm what that construction is. Exotic woods, bamboo, things like that have different surface temperature maximums, different R values, and just because it looks like wood and it smells like wood doesn't mean it's a hardwood. A bamboo is a different type of, and a lot of people are using this because it's a renewable resource and it's affordable. But whatever it is, you end up with different R values, and you need to know what those are so that we can design our systems around there. So just getting this information up front is very helpful. Carpet and pad, you can totally put carpet and pad on top of radiant. But they make a radiant rated pad. It's a very dense, rubbery pad that transfers heat and has very low resistance. That's not a problem at all. But if you go, the customer, you install this system, your customer goes to Home Depot and gets their free pad and throws that free pad underneath there, puts their carpet on. It took me several days of research to find out what the R value is of that free pad, and it's about 4, which is how many times more than the R5 that we calculated in our original design. So you got a guy that wants to put carpet and pad down. That's fine. Let's just advise him that he needs to use a radiant rated pad or no pad at all. That's fine. You can go without pad. In our offices in Auburn Hills, Michigan, we got 20,000 square foot of radiant, and we've got carpet glued right down to it because it's commercial carpet, it's commercial application, it works great. So no matter what floor covering is, you can do some research on the web, go to an industrial website, make a phone call, find out what that R value is so that when we do our design or when we do our final check on that design, we have the information we need to be able to get it done properly. So starting in some of these best practices. So concrete wet slab, this is probably, if you're not into radiant and you hear about, I'm going to do some radiant, this is probably what most people think of. It's a cement slab with tubing in it on top of some wire mesh and some insulation. And this is still probably the most common. You can put this in warehouses and pole barns. It's all over the place. But if you don't install it properly, it won't work properly or it'll waste a ton of energy. So we want to make sure we follow guidelines. And this is probably one of the biggest issues is you need to put insulation underneath here. In some municipalities, there's no radiant code. A lot of them, there are a few states that have adopted the radiant code. But what the radiant code says is the minimum is an R10, a 2-inch foam. That's what's best practice. That's what they want. That's going to be an R10 below. So when we put our resistance above it, we want to be less than that, significantly less than that. It'll force the heat up, and we want to have that thermal break. But the biggest thing people sometimes forget is this perimeter insulation. If I heat this slab up, 140 degree water, I got 85 degree surface temperature, and I don't put this insulation here, it's going to touch that footing and it's going to bleed energy into that footing every single time it comes on. And how much energy does it bleed? We don't know, but I've had experience with, not myself, but other designers, where they get called out to a project, it's not heating. It's not heating. You design this and it's not heating. Find out they skipped that step right there. They got a 4-inch slab pushing up against the footings. It's bleeding energy, and you get a green ring around the house in the middle of the winter because it's keeping the soil at about 50 degrees and the grass keeps growing.
Tulips popping up in February.
Yeah, so that's a big deal. You forget to do that, you can have an issue with it. Forget to put insulation underneath it completely, you can have even more of an issue. Sometimes the system, the boilers are oversized, you can just keep cranking the temperature up and you get lucky. But rather than getting lucky, let's just remember best practice. Put my 2-inch foam underneath here, put my perimeter insulation down here, and this is just good craftsmanship. If you cut that on a 45, it's going to look like the cement slab is poured all the way up against that footing, but it's not. It's not going to bleed energy. I've been on a couple projects where they did this and they just left the 2-inch foam all the way up. It does what it's supposed to do, but there's always crack and stuff along the edge of the warehouse where that's at. So best practice, cut it at a 45, put it in there, make sure it's there. Tying the tubing down to wire mesh or rebar, this is the way it was done 10 years ago, 15 years ago, 20 years ago. But there's some things you need to do is you need to tie it to there. You need to tie it down tight, and you got to put a lot of zip ties or wire ties in there. This is a ton of them, thousands and thousands of these. The very first radiant project I ever did, I went to go pick up the material, and this guy tried to sell me like $1,200 worth of metal ties. And I'm like, I'm not paying $1,200 for those. I'm going to go buy some zip ties. So I went and bought about 400, 500 zip ties, took them out to the job, and the guys were like, we need more zip ties. So I went and bought 400 or 500 more. We need more zip ties. And they ended up using about 4,000 zip ties on this project because that's what you need. If you don't zip tie it down, when they go and float the cement in there, it's going to push the tubing around, it's going to float up and down. Another thing, this is an example, maybe hard to see.
Cut those tags.
Didn't cut those tags down. If those tags are sticking up through the cement, it's not going to hurt anything. It's really going to look bad. Someone's got to go down and cut them all and grind them down. So not only put them in, but cut them off. If you're using the metal tags, you can push it down, they stay down. But zip ties, you want to make sure you cut them off. You can do staples. Staples is a great way to go. You're going to go ahead, lay all the tubing out. Rather than putting it onto the wire mesh, you're going to put it under the wire mesh. You're going to staple it to the foam. The cement guy can go back and put his wire mesh on top of that. It's perfectly fine. This is a lot faster than bending over and doing zip ties or wire ties. It's probably not any more expensive than zip ties or wire ties though. And if you get a nice stapler like this, you don't have to bend over. You can get it put in quickly. This is not necessarily a best practice, but it's a smarter practice than zip ties or wire ties. There's availability for these track systems. You can staple these tracks to the foam, and then you can put your foam in there. What's nice about this is it's easier to space your tubing and make it more accurate. You can put it down and just put a few staples in between here. When you pour it in, it looks nice and neat. It goes in simple, it goes in easy. One of the things you need to be concerned about is expansion joints and contraction joints. So there are some control crack joints that will be put in a driveway or in a garage or in a cement slab. And those are just where they cut through the top surface and then we'll control where that's going to crack. You need to put some sort of a protection, a piece of corrugated plastic on there, because if you've ever seen cement when it cracks like that, it is razor sharp. And it moves a little bit, expansion and contraction as that thing heats up. And if you've got just 2 razor sharp pieces of cement moving up and down in your tubing, you can damage it and it can fail. And then you got to break it up. So making sure that anytime that there's that control crack, you put that in there. If it's a true expansion joint where they're putting felt and they're separating those 2 slabs completely, then you need to go underneath that completely. If you've ever seen, if you live up in the north, you'll see frost heave come up and 2 slabs will be next to each other. One could heave 2 or 3 inches above the other. If you got your tubing running straight through the middle of that, what's going to happen to them when you get that frost heave from one slab and not the other? It's going to destroy that tubing. So anytime there is that true control expansion joint, you want to go underneath it. This slab can move all at once, and the tubing is protected and it won't have any issues. Usually on a commercial print, if you're quoting a commercial job, they're going to show you where those expansion joints are. Not to control cracks necessarily, but those true expansion joints are there, and we're going to design around them. We're not going to have 60 tubes running across that joint. We're going to run the tubing parallel to it so that we're not crossing that joint as often. Unfortunately, sometimes as designers, we may not know where that is because it's not in the print. So again, if you find out, hey, it would be really good if the tubing was running the exact opposite way. You can call your designer up. If we're using LoopCAD, it's not that difficult to push a button and let it run the other way. And then you can have a drawing on the wall that exactly represents what you're putting in. Two bend supports are a huge deal. For the same reason, we took protection sleeves anytime there's a control crack joint. If you don't put these two bend supports where that tubing comes through cement, that cement connection right there where the tube comes out is going to be razor sharp. And PEX tubing expands and contracts. Anybody ever looked at a PEX job after the hot water's run through it? It doesn't matter how much time you take to put that pipe in straight, you run hot water through it and it expands and moves. Anybody know how much PEX expands? I'm going to tell you because that's what I'm here for. PEX tubing, half-inch PEX tubing, I only know the numbers for this. If I take 100 foot of half-inch PEX tubing and I raise it 10 degrees, it's going to grow 10 inches. So if I take a 300 foot roll of half-inch PEX tubing and I raise it 10 degrees, it's going to grow 30 inches. What if I raise it from 30 or 70 degrees to 140 degrees? I'm sorry, it's 3 inches per 100 foot. So a 300 footer going from 70 degrees to 140 degrees is going to grow about 21 inches. 21 inches is a lot. And if I've got all of the tubing encapsulated in cement, because it can't expand and contract, where does all that expansion and contraction happen?
It's going to stay in compression.
Slab. Exactly. It's stuck in the slab. It's not going to go anywhere. But where that tubing is coming out of the slab, there's going to be some movement in that tubing. And if I don't have a tube protection sleeve protecting them from moving around, I could have some issues. You know, it's just, it's required by the codes if you have a rating code, but it's just best practice. This contractor did a great job. He also put insulation in each one of those things, which is a great best practice. And the only reason for that is, if you've ever seen them pour cement with the wheelbarrows, and they're just running around doing this, if they do that onto your nicely installed tubing with two protection sleeves, and the cement goes into those two protection sleeves, you don't have two protection sleeves anymore. You just got a sleeve around some more stuff. So, not a bad idea. I never saw that before until I saw this contractor do it. I'm like, that guy's got burned before, and he's adapted to the new best practice. So, good thing to think about. If you've got a second floor steel deck type of a system, same exact principles apply. I'm going to put this stuff on a steel deck. I'm going to make sure I insulate underneath it because I need to have R value. But I'm going to put it down in some wire mesh. I'm going to make sure that I put the tubing in and zip tie it down. Anytime you get an underfloor type of a situation, an overpour, staple down in a residence, or even a commercial building on a metal deck like that, you need to secure the tubing down. If it's a metal deck, we're probably going to do zip ties onto some wire mesh. If it's a resident where we can staple down the tubing, we want to make sure the staples are not crushing that tubing. If you've got an old stapler that staples into wood, those are calibrated, you can adjust them. But if the staple comes down and it pinches the tubing, it's not intended to do that. It's intended to hold the tubing in place until the cement's poured so that it doesn't move around. So making sure that there's a small gap and the tube is not pinched in there and it can move freely is a good best practice to do with that. You know, doing lightweight concrete, you want to make sure you're insulating underneath. The same reason we put R10 foam underneath the slab, we're going to put insulation underneath it, suspended like this, because we want to drive the heat up. We want to make sure there's enough R value below it so that our tubing will be going up. Lightweight concrete jobs, this is a good best practice that I learned. There's gypsum and there's lightweight concrete, and they're not the same. They got completely different R values, they got completely different installation practices and everything. But lightweight concrete is not lightweight at all. It's 17 pounds per square foot. And most of the time in a retrofit, you can't do this without, you know, re-engineering the floor, putting in bigger floor joists and things like that. So if you get a customer that says, can you come in and put radiant in my house, I'm remodeling it, and we want to just do an overpour, get an engineer involved, because you could go in and do that and end up the whole house sagging and failing.
But the water weight in the concrete, you have to figure that in. It's not just the weight of the concrete, it's the weight of the concrete plus the water.
Yes. I've seen a project where they dumped a bunch of concrete onto a second floor, and they point loaded it while they were doing it, and it just, whoa, I thought it was gonna be a bad failure. So, you know, lightweight concrete, great for new construction, as long as they've engineered for that weight. Not so great for all retrofits. Maybe a bathroom where they're going to put a little bit of a mud bed in there. That's different than a whole house being poured like that. And again, with gypsum, gypsum is not concrete. You don't really trowel it out. It is like a milkshake. You know, you got to prep the floor. Most contractors are not going to go in and do gypsum. They're going to hire a gypsum company to come in and do it. But you got to prep it. And if you're prepping a gypsum project and you don't dam off those tubes right there, or any place there's a penetration in the floor, stuff's like a melted milkshake, it's going to go right down through there. So you got to make sure you really prep your floor well, and then make sure that they install it properly when it goes in. Dry systems, this is anything that doesn't use cement. So there's over the floor dry systems, there's under floor dry systems. And you know, there's just some good practices you can do that. If you're doing underfloor dry systems, we always recommend heat transfer plates. If you just staple tubing to the bottom of the floor, it doesn't really transfer heat really well through there. There's techniques where you can do staple up. You can put an air gap in there, and you can heat that airspace, and that airspace will heat through the floor. But some guys will just staple tubing to the bottom of the floor and put insulation up there. And that's not a great practice. You're not going to get consistent heat and all through there. And when you're doing heat transfer plates, you know, the technique for installing them is, this is a simple one zone. I'm going to go ahead and I'm going to run all my heat transfer plates. I'm going to install them. And these heat transfer plates have holes pre-drilled in them. We're not shooting them with nails. And if it's got 10 holes that are pre-drilled in there, you need to put 10 screws in there. Because the way a heat transfer plate works is it's in contact with the floor. It's in contact with the tubing, and it's going to conductively transfer its heat from the tubing to the plate to the floor. And if you got only 2 screws in a 10-hole plate, it's going to expand and contract. It's not going to touch the floor. You're not going to get great contact or conduction. So make sure you put your plates in there. Make sure the ends of these things are not pinched and tied tight. You know, when tubing expands and contracts this is a good example. In this situation, you could be going from 70 degrees to 140-degree water. It shuts off, gets down to about 70 degrees in there, it kicks on, 140-degree water is in there. You got a 300-foot loop that's growing 21 inches. In this situation, it can flop around. If you've got areas for it to expand here and back in here, it will, and it can eliminate some of that ticking sound that you will get in those heat transfer plates. If you pin down here with a staple and pin everything down here, it may look cool when you install it, but when that tubing heats up and it starts to expand and contract, it's all pinned down and won't go. Yeah.
It'll break the staple.
It'll break the staple. It will. So making sure that you install it. Best practices. Make sure you leave room for expansion. Make sure you have that slack in there, and make sure you get it all back to there. Buying cheap stamped metal plates that don't have performance charts. It's kind of hard to calculate what your output's going to be unless you have a true submittal sheet that says at this water temp you'll get this output, depending on what's going on. So, going online, reading about, you get a lot of guys. I can do this myself. I can do it for like $3,000. I can have this heating system in my house. And then, what's your output, what's your water temp, what's your flow rates. You really won't know that. So hopefully a contractor's not doing this for somebody. Some people might try it on their own. Taking a heat transfer plate and getting your tubing in there properly. A lot of these heat transfer plates, all of them in the industry, have an omega shape in there so that the tubing is forced into there and it's tight. Again, this tubing has to transfer as much heat as possible to this plate. If you don't get the tubing installed all the way and you have that gap in there, you're not going to get the heat transfer that was expected out of there. Your system may not work the way that we designed it. So just taking the time, using a rubber mallet. I've seen some guys that use some rubber nailers, and they'll put an end on it, and it'll just push that tubing into that track as you're going along. Big important thing to make sure that you get that installed, because if you spend all the money on the tubing, you take all the labor to put the plates in, and then you skip on this little step right here, your performance can suffer.
Oh, the plates are more expensive than the tubing.
Plates are very expensive, but it'll get you a design that you can rely on. Just examples of what not to do.
What's that, Radiant Tech?
stapling this up and running the holes. They followed pretty much every best practice that there is, except for the fact that they didn't. So, just an example of what not to do. Then, putting some bubble wrap underneath there on these joists and putting some tubing in there. That'll be a nice warm space for rats and things like that. But I don't know how much heat you're going to get through the floor above it.
180-degree water through that.
Yeah. Heat transfer plates, these are fine, but this project is actually, this is a porch. This is a vault below a porch. They were trying to stone out the porch above it. Staple the heat transfer plates, or not staple them, they actually used like a Remington shotgun, got them all up in there. Did a great job here, left this nice and loose, because that's what they're supposed to do, allow for that. But I don't know what the transfer is through 4 inches of concrete into the, it might melt snow, it might not, but probably not. But the area below there could be warm. But anyway, even if they did that all, you got to insulate below that, because the R value of that cement is much higher than no R value below. So making sure you're insulating below a situation like this is always important. Pipe layout guidelines, these are best practices. As installers, I try to follow these because I know when you're in the field and you're installing this, you're going to install it the way that it needs to be installed. But we want to make sure that we're trying to put in the easiest install possible. Counterflow spirals are awesome because they evenly distribute the heat across the room. You don't feel the delta T. If I got water coming in at 140 and leaving at 120, in a big room like this, you might feel that difference. In a small room, you wouldn't. But I've done a handful of designs drawing this counterflow spiral, knowing afterwards, not knowing enough, but realizing afterwards, that's how it was installed. Because that's very difficult. You're not just going to loop that thing out, loop back in, and go to the other room. It's a lot of thought that goes into that. You may have to reposition it several times. So unless somebody says, I want that, I'm going to design it that way because it's easier to install and it's going to be installed that way. Making sure your manifolds are
Just
located.
going back to that, has anybody done any real, like, either floor image testing or anything to see between counterflow and serpentine, what's the real delta T on either side of like a typical room, which is like, 20 BTUs per square foot. We've got, delta T's in the order of,
I feel like I've seen pictures of that.
Yeah.
Sigenthal or Houlihan or somebody did it.
Right. But I'm like, do you really get a significant delta T, or is it like, it's like, we want to do that, but realistically in practice, a counterflow, we're talking about
Somebody
like
said it was good.
1 or 2 degrees of
Yeah.
difference.
Somebody said it was the best way to do it, and so people have followed
Right.
that practice because it was the best way to do it. But it may not be practical to do it that way. Making sure your manifolds are located in reasonable spots. You get a lot of guys that will call up and say, hey, we're doing this design. We need 4 zones, 4 manifolds, and we want every manifold back in the mechanical room. Well, that's very difficult to do because a 1/2-inch loop is typically around 300 feet. If the mechanical room is 100 foot from that room, I can run 100 foot to it, 100 foot in there, and then 100 foot back, and that's 300 foot. And how many loops am I going to have? So we tried to design with remotely located manifolds that make sense, making sure that we can only have long tails running down hallways or through rooms that we don't want to heat. Because we're trying to watch our circuit length, and typically, these are best practice lengths, and this is designed to keep the pressure that you have to push the water through the head down to a reasonable number so that your typical pump off the shelf or circulator off the shelf will be able to do it and keep us in the right head range for that. So for 3/8, we're going 250 feet, 1/2-inch 330, 5/8 400 feet, 3/4 500 feet. If it's 1 inch, I can go 550, maybe 600. But if I'm using design software, no matter what I put in there, it's going to calculate out what that head is so that I can know how to size my pump. But what I found out the hard way was I could go 330 feet with every loop. Pumps can usually handle it. So I was designing stuff to 320, 325, and then I'd have this smaller contractor that would say, great, I can't handle a 1,000-foot coil. What am I going to do with a 1,000-foot coil at this tubing? I can't carry it. If I lay it on the ground, I can't pull tubing off of it. So then I started realizing best practice, I should probably find out what the contractor prefers before I design it. Because if I design it all with 320-foot loops and he buys 300-foot coils, what's he going to do? he's gonna completely take the whole design I gave him, throw it out, and just do whatever he needs to, and then my design's useless. So, because of that, we're always asking, do you have an uncoiler? What do you prefer coil size? So now I don't design to 300 feet even, I design to 290, 295 max. That way, a 300-foot coil will be able to satisfy every coil, every loop in there. And if the manifold moves 2 feet this way or 2 feet that way, you should be able to handle that in the field. Again, 5/8. I have a contractor in Minnesota that loves to go 500 foot with all of his 5/8 coils. And he's successful with it. And I challenged him on it, and he found this document that was about 25 years old that said maximum length for 5/8 is 500. And he's been running with that ever since then. Super successful. So if he wants me to design something, I'll go to 500 foot for him. But you know, just knowing what should be there. But consider those coil sizes when you're doing your design to make sure that you're giving the customer or the end user or the installer what they want. Again, if we have a room that we know we're going to have greater heat loss on the outside, I can do, you know, different perimeter spacing. If you're using design software, this is super easy to do. If you're not using design software, this can be a little more difficult because how do you calculate how much tubing is in there? You know, I can use certain formulas to figure out at 12 inches on center, I need 1 linear foot for every square foot. But now what do I do when I've got 3 foot in there? And it makes it a little bit harder to calculate it out. But if we know we're going to need some extra BTUs, we want it to be on the outside wall, we can go for a design like this. Also, when we do, we select our manifolds to be in remote locations. That makes it a great install. I don't have tails running all over the place, but I also want to make sure that any loops in this room don't bleed over into this room. So I might have unequal loops. If you look at them, these aren't all 300 foot or 289 foot. Oops. Went really fast there, didn't I? All right. So a lot of different loop sizes, but if I only keep these loops in this room and run them back to this manifold, this room right here, all of these loops only are in this manifold. If I have design issues where I got too much heat loss here or not enough here, I've got circuit actuators here. I can put a thermostat in that room. I can use a thermostat and a circuit actuator to control the flow to that room and do some stuff, not just adjust flows, but actually turn them on and off and turn them into separate zones, which you can take care of a lot of that. You know, if I take this hallway right here, I got all this stuff in here, up into this room right here. If I bleed into this room, I lose control. So if I'm keeping all my loops in each room as it should be and keeping them all separate, I might have 150-foot loops here, 200-foot loops here, 280-foot loops there. But if I've got a manifold with flow meters and I get a design software, I'll know what my flow rate needs to be and what my water temps need to be. Again, I think we already said this in another slide. You know, the easier install is the better install. Making turns back and forth a lot is a little bit harder for the install. So I want to draw it the way that I think it's going to be installed, not just whichever way the computer tells me it should go first. If I have a room with multiple loops in it, you know, this has got a 220-foot loop, 222, and a 224. That room is somewhat balanced without me doing anything to it. You know, I could go 300 foot, and have like a 90-foot loop left. But that's not best practice. Best practice is to balance the loops that are in that room. I could put a simple manifold in here, a 3-loop manifold, and all the flow should be balanced, and I can control my flow into that manifold that I want it to. But making sure that I keep those loops balanced will make it easier. If you're coming out of a manifold, this is especially when you're in a cement slab, spread that tubing out as quickly as possible to the design spacing. Anywhere that these tubes are, when I'm coming out of cement, that's going to be a hot spot. That closet's going to be cooking all the time, and we want to make sure we spread it out so we don't have a hot spot in that floor right off that manifold. If I'm designing a system and I'm right on the edge of exactly how many BTUs are there, or I'm even short, maybe 1 BTU per hour, you know, I can put more tubing in there, and I could overcome that possibly just by doing that. But if I keep everything 12 inches on center in here, and I fall short, I may have to raise the temperature to adjust it. I may have to do other things. If I go to 9 inches on center here, it might allow me to lower that water temperature and adjust the flow and keep the temperatures in that area about the same. Again, we talked about this. If I know that there's going to be an expansion joint right there, I'm going to design my system around it. So I'm not crossing that expansion joint more than I have to. It makes it simpler and easier to get a better install. Stay 6 inches from walls when I'm putting stuff in. Never cross your tubing. You don't want your supplies and your returns crossing. So just, lay it out so that that's not a problem. Loop 1 here, loop 2 here, loop 3 here, running up into the manifolds. Make sure you know your floor coverings eventually. We talked about that. What's your floor covering and R value? Especially for dry systems that are above the floor, below the floor, making sure you're insulating below that. The higher water temperatures, less tubing. If I could put more tubing into a floor, I can lower my water temperatures. How many of you guys are using modulating condensing boilers? If you're using a modulating condensing boiler, you want your water temp as low as possible coming back. That's going to make that boiler condense. It's going to rinse the heat exchanger. It's going to run really well. If I'm running 12 or 18 inches on center on a pole barn in the middle of Indiana, and I have to run that water temp at 170 degrees, and it's coming back at 150, that modulating condensing boiler is never going to condense. Probably fail in about 3 or 4 years. They're going to blame the manufacturer, and he's going to fight it. And really what it was you didn't really design the system well. You should have put it at maybe 9 inches on center. Could have got that water temp down to 130, 140. Then the water temp coming back is maybe 120. Could be as low as 110. That boiler is going to condense like crazy, and it's going to do well. And if you get it designed, you get it done through a designer, get a printout of it, put it on the wall, and as you're installing it, make changes as you made them so that you got a record of what went on there and you've got an as-built of that project. It doesn't seem like maybe in a house or a pole barn they don't need that, but you should do it. Keep it in a file. If you ever have to go back and work on that thing in 5 years, 4 years, 3 years, 6 months, you can pull it out and go, oh yeah, I know where everything is. I kind of remember what's going on here. I've got a record of it. Taking pictures is not bad. How many people have a phone or their camera? Everybody. Take a few pictures, put that in a file, and have it on a file there for it. Using an uncoiler, as I mentioned before, some people don't want to use large rolls because they can't use them. Well, you can get the project's costs down significantly if you can go with 1,000-foot coils. Because 1,000-foot coils, I can get, not only if I'm using 300 footers, that's fine, but if I can get up into the higher rolls, I'll have less waste on that project, and I can make it do well. This is probably the best uncoiler in the industry, and if you've ever used a flat uncoiler, anybody ever used one of those? You put those things down, and as you're pulling the tube off, I don't know how it happens, but the thing slinkies up on you, and you're trying to do this, and you're trying to put the tubing down, and it's a nightmare. You get a nice uncoiler like this, when that happens, you stop for a second, you pull a pin, you can spin the coil around, and you can get it all sorted out, and then you can start going again. I don't know what it is, it's like a physics thing, that if you take tubes that's in a coil and you start pulling straight, it slinkies up on you. And there's the only way to fix it on a flat uncoiler is to lift it up, and you and your buddy uncoil it, which I've done a couple times, and you realize you're going the wrong way, and you're like, ah, and then you start going the other way. And you get it all figured out. So one of these, they're very expensive. These can be $1,200, $1,500, $1,600. If you're doing these projects enough, having something like that is going to make your life a lot easier and make it super easy for your installs. Plus, it'll allow you to use longer coils. Having a new tube cutter, big deal. You know, if you cut your tubing square, you're going to go ahead and put those fittings in there. I had a bunch of plumbers that I used to supply these to, and they used to always order new blades because there was chunks missing out of the blades, and I could not figure out how in the heck would you get chunks out of blades. You're cutting CPVC, you're cutting PEX, and I was working with the guy one day, and he was putting the toilet in, and he's going along, and I hear a click. I'm like, what the heck was that? You know, the toilet bolts that have the little ring in it? He was taking his cutters and using those cutters to cut grass with. And there was chunks missing out of it. And then he's cutting PEX with it the next day, the lab supply, and it's all jagged. So, just, you learn things the hard way, and sometimes, so don't use these to cut closet bolts, but it's not a big deal. 15 to 20 bucks, you get a brand new cutter. Every cut you make is clean and smooth, and you can use that cut to hook up tubing. Doing an air pressure test is a must. You know, you should take that gauge, you should plug it in, and not just do an air pressure test, but install the manifold, run everything to that manifold, and use the manifold to do the pressure test. I've seen so many people that will make a temporary manifold out of PEX fittings, and they'll spend an hour putting all these fittings together. An 8-port manifold is going to have, you know, 16 connections, or 16 T's, which is times 3. I can't even do the math. It's a lot of connections. It'd be crimping or cold expanding. And then when you get done with it, you just throw all that stuff away. If you install the manifold and pressure test through the manifold through a gauge like this, it'll be pressure tested, and the tubing will be installed into the proper loops because you got it all hooked up like that. And then you can leave it under pressure, and you know, until it's ready for commissioning. You should always leave your system under pressure. If you walk away from that system and you come back and notice that there's no pressure anymore, somebody probably hit it. Pouring guy, I would blame him. Maybe the heating guy going in there putting the ducts in or something like that, or the electrician. If you notice that it's down, I did pressure tests in a building. We went back 4 years later to install it, and they were still holding pressure, which told me that we don't have to worry about this system. We can bleed out the air and commission it. Using design software is a must. If you were in a session this morning, it was really great. You know, you can take the design software, you can draw a visual representation that's accurate and scaled. You can take that information, you can mess around with different loop layouts to figure out what's best for you. You can rotate it right, left, counterflow spirals, double serpentines. You can do all that sitting at a desk in minutes. That would take you hours in the field. And this way you can figure out what's the best way to go. You know, you get all of your information that you need for heat loss calculations. There's no guessing. I'm not going to go into a house and say, I think I'm just going to do 20 BTUs per square foot here. This is going to take you, you're going to put in the actual location that you're at. It's going to give you a true heat loss for that building, and it'll tell you how much, what temperature and BTUs you need for it. And then to be able to analyze your whole project. You know, rather than putting the system in, commissioning it, and then coming back and adjusting it later, I can go through these steps here, and I can see which rooms are going to overheat ahead of time, and I can make steps before it's even commissioned to overcome that. And just to be able to look at a building and see exactly what it is. Luke has the ability to do a 3D view of that building, spin it around, make sure that you got your heat loss done properly. It's a big deal. And then just a few more design considerations. You know, a simple room like this, if I say I want to have equally balanced loops throughout there, I can install all my tubing like that, all under just under 300 foot loops, and it's perfectly balanced. But if I take that same project, you know, picking a manifold, and I take that same project to 70 by 30 room and I put walls in there, if I just run my tubing like that, it will probably heat up and be somewhat comfortable. But, you know, the heat loss over here is not the same as the heat loss over here. And if I install my tubing like this, I have no way of making adjustments in that system. You know, these loops are on or off. There's no way to zone it or do anything. So, you know, taking the same project like this and just breaking it up into 300 foot loops, but try to keep all my coils without all my loops and keep them 300 foot, but not go underneath any walls. A little bit better. But, you know, I don't have control because this loop bleeds into 2 rooms. Plus, what's going to happen to this little mudroom, mechanical room, anytime there's a call for heat?
That's where the dog's going to sit.
It's going to just cook like crazy in there. So this is better than just 300 foot loops everywhere. But, you know, it's balanced, but I still don't have as much control. But if I put remotely located manifolds, this is the same thing. I now have total control over every one of these rooms because these 3 loops can be zoned out back to this manifold, these 2. But again, installing those tails is very difficult. This hallway is going to be cooking. This mechanic room is going to be cooking. Better control, but not a better design. If I take a manifold with flow meters on it and I can put some remotely located manifolds, one in the bedroom area, one in the living spaces, and now I'm running that out. Now I've got all of these rooms individual, but I can control each room individually. These 3 loops can be a zone. These 2 can be a zone. This foyer area can be a zone. Each bedroom can be a zone. Or I could just make the living spaces one zone off this manifold. Everything off this manifold can be a second zone. But if you install the tubing like this, You can go one zone all on, 2 zones on and off, or I can break this thing out with circuit actuators into 7 different zones. As long as you install your tuning like this, you can make those choices later. If you just put a bunch of loops in there, it limits what you can do. Mechanical rooms, we're not going to talk about it, but there are a bunch of best practices in the mechanical room. And that's something that if you're going to get into boiler replacements and some of these retrofits, you really should think about best practices for this piping in here. I'm not going to talk about it today, but there are a lot of information out there on closely spaced T's, hydraulic separators, air and dirt separators, magnetic separators, all things that should be used when you're doing a boiler replacement in a mechanical room in a radiant system. Something that you can look forward to, this is the latest edition of the RPA guidelines. It has a lot of this information on it. In the RPA, we just redid it, and there's a 2025 version that's out. I think it's available any day now. And if you are doing any radiant installs, you should get one of these and just read through it. It's got a lot of the best practices we talked about here. It's got that information. If there's what this has been used for a lot is if there was no radiant code, this is what an inspector might hold to see if you did what's best practice at least. And that was not really a code book, but it was something that a lot of people would use as a code book or as a radiant Bible. So if you want, go by booth 2175, talk to those guys about it, find out when it's available. I think we're giving it away for free. If they say who told you that, tell them it was John Mullen. He's the director, but it should be available. I'm kind of excited about it. We worked on it for about 7-8 months, back and forth, about 6 or 7 of us going through best practices. We added in some stuff about using computer design software. We added some cooling system information in. There's some best practices for that. So great opportunities there. And if you have time to come by 1791, that's where our Legend booth is. We've got a bunch of new products in there, including carbon steel gas. So, any questions, comments, concerns? Awesome. Well, I appreciate you guys coming. This is way better than my first presentation with 0 people in it. Glad you were here. I hope you learned something. If you got any questions,